Welcome back to another demo. Today we'll be looking at how to understand Young's modulus using a slinky.
First, let's look at the slinky like a spring. If we have a slinky hung vertically and then put some weight under the spring, it'll elongate from its original position to now position D. If we put twice the weight, it'll then elongate to a different length. And of course, if we have a stiffer slinky with a higher spring constant, the elongation will be less severe. We may have already learned about this phenomenon from our high school physics, and it's called elastic deformation. Turns out, elastic deformation is more general than just slinkies, and it applies to all solids. Looking closely at the slinky, when elongated, you can see each layer of the ring separates quite evenly. Similar behavior would happen in solids when we deform it with a small force. At the atomic level, the bond between each atom will separate evenly, causing it to elastically deform. If spring constant K is a parameter that describes how stiff a slinky is, then Young's modulus is a materials property that describes how stiff the atomic bonds are inside the solid. It measures the stiffness of a solid material. The equation for Young's modulus is stress over strain, where stress is force over cross-sectional area and strain is change in length over original length. Now, let's take this demo a step further. You may have learned that sound waves are mechanical waves when atoms in air/water interact with each other with a sequence of compression and tension. Turns out the concept of acoustic waves is more general than that. It's a form of a mechanical wave with the progression of stress and strain inside a medium. All mechanical waves can also propagate in any solid. Take a slinky, for example. When a pulse is sent from one end of a slinky to the other, it'll take some time to travel to the other side. The propagation speed of this pulse is called the wave speed or speed of sound. You may have already learned about the concept of the speed of sound, and we may already know that the speed of sound in water is faster than in air. The reason for that is because the atoms in water are more tightly bounded than that in air. In other words, you can think of water as stiffer than air. Similarly, the wave speed of a slinky is governed by its stiffness and how heavy the spring is. In solids, the wave speed is now governed by how strong atoms are bonded together and how heavy these atoms are. In other words, the speed of sound in solids is governed by material properties such as Young's modulus and mass density.
Speed of sound is a very important acoustic property when designing musical instruments. When a musical instrument, say a guitar string or tuning fork, oscillates, the faster the wave speed, the higher this oscillation frequency. For example, steel tuning forks are higher pitched than copper tuning forks. Steel has a higher Young's modulus and the density of the materials is similar. Atomic structures with a higher Young's modulus lead to higher pitch. Furthermore, think of bells. Bells have to be made of certain materials to make the correct sound. Typically, they're made of steel, brass, glass, or even pottery, but they're not made of a polymer, which has a significantly lower Young's modulus. Thank you for joining me to learn a little bit more about waves and Young's modulus, and I'll see you on the next one.